The 100-meter radio telescope in Effelsberg, Germany. As one of the largest telescope dishes on Earth, it is capable of detecting radio waves that have traveled billions of years from the farthest quasars and galaxies. The larger the collecting area a radio telescope has, the more sensitive it is to signals from the cosmos, enabling observations of fainter sources. Greater telescope size also results in sharper images with better resolution.
Obviously, there's a limit to the size of a telescope that we can build. Fortunately, we have a trick for that. It's called interferometry.
Using a technique called interferometry, multiple telescopes simulate a single larger telescope. They observe the same region of the sky at the same time, gathering data. This data is sent to a supercomputer called a correlator. The correlator synchronizes the data for every possible pair of telescopes and combines them all to create a single image. Interferometry can also be done on a scale of thousands of kilometers. This is called Very Long Baseline Interferometry, or VLBI. The European VLBI network is a collaboration of major radio astronomical institutes in Europe, as well as Asia and Africa. With access to 27 telescopes in 13 countries, the EVN is capable of simulating a telescope up to 10,000 kilometers in width, nearly as big as the face of the Earth. With so many stations at such great distances, the EVN can produce images with better resolution than the best optical telescopes.
VLBI gives us fantastic resolution. In fact, the resolution is so good that even in astronomical objects we can see things move. That is something that is hardly possible with any other technique.
As with smaller interferometric arrays, VLBI data is sent from the telescopes to a correlator. The EVN correlator is located here at the Joint Institute for VLBI in Europe, or JIVE in the Netherlands. Specially built for this purpose, the correlator is continually improved to ensure compatibility with upgrades made at the various telescopes. Correlator upgrades also enable cutting-edge capabilities to support new astronomical questions, such as when and how the first galaxies were formed. In traditional VLBI, data is sent from the telescopes to the correlator on magnetic tape or discs. Shipping discs here from around the world is costly. They can be damaged or lost in transit, or can be found to have errors in the data. Moreover, there is a significant delay from the time of the observation to the receipt of processed data by the astronomer. In addition, scheduling VLBI observations typically requires significant advanced coordination among the many institutes that operate the telescopes. This limits opportunity for unscheduled observations when transient events are detected, such as supernovae and other violent cosmic phenomena, until now. In recent years, JIVE has made numerous updates to the EVN correlator. The most significant allow for data to be streamed over fiber optic networks directly to the correlator.
This technique is called real-time or electronic VLBI, or eVLBI for short. And we use this technique to stream the data from the telescopes directly to the correlator, where it's correlated in real time.
With such fast data delivery and processing, problems at the telescope stations can be detected and corrected immediately, saving valuable data. Astronomers receive their data in a matter of hours rather than weeks. Furthermore, procedural changes make it possible to accommodate observations on short notice when transient activity is detected.
Some of the most interesting astrophysical phenomena are transient, and many of these are located at great distances from us. To study emission from objects like collapsing stars or accreting black holes, radio astronomers have to arrange observations with the largest telescopes on a very short notice. Real-time eVLBI at the EVN makes this much easier than before, allowing us to observe many more transient sources. In the past years, we've been able to investigate a number of supernovae, which are exploding stars, microquasars that have highly collimated relativistic outflows, or even a star that have been ripped apart by a supermassive black hole.
These upgrades were made possible through the EXPRESS project. Coordinated by JIVE and funded by the European Union, EXPRESS upgraded the correlator for real-time processing. It also completed much of the last-mile networking to connect the telescopes.
Data from telescopes all over the world is streaming into a hardware supercomputer, which is at the core of our VLBI operations. And what you see on the screen here is the total data rate that has been coming into that.
Now, eVLBI is a regular service offered by the EVN. eVLBI observations have already led to scientific discoveries that have improved our understanding of how galaxies form and evolve. Improvements in the past few years have made eVLBI as good as traditional VLBI in terms of bandwidth and image resolution. Today, JIVE is working to make it even better. Major efforts at JIVE are focused on a new correlator platform required for increasing data rates planned by the EVN. JIVE and EVN engineers are using the latest electronics to deliver the processing power for future radio astronomy observations. In 2010, JIVE started coordination of the EXPRESS project. With 14 partner institutes, JIVE is combining the best of both worlds, the speed and flexibility of eVLBI with the robustness and reliability of disk-based recorded VLBI. One main activity of the project addresses network disruptions to make sure data transport progresses smoothly. Data integrity is protected by buffering the data at the telescopes and the correlator. Related upgrades will improve on-the-fly monitoring and modification. This will enable automated correlation. Another NEXPRESS activity is to make more efficient use of the networks with bandwidth on demand.
Right now we have static light paths for eVLBI, which are point-to-point connections. They're there all the time whether you use them or not. So this is not a very efficient use of resources. So we're developing bandwidth on demand, which makes it possible to dynamically allocate bandwidth at the times that you need it, and not at the times that you don't.
Moreover, dedicated light paths are limited to 1 gigabit per second. The EVN is already planning 4 and 10 gigabit per second upgrades. A third aspect of the project addresses the limited speed of the existing centralized hardware-based correlator. In recent years, JIVE has developed a software correlator, the basis for an automated distributed correlator. By leveraging network and computing resources that already exist in the EVN, NextPress will enable additional VLBI observations with minimal impact on scarce resources. The last major challenge to combining traditional and eVLBI is in storing and archiving the tremendous amount of data generated during an observation. A typical EVN experiment generates 12 gigabytes of data per second. That's about the same as one high-quality feature-length movie every second for 12 hours. NextPress is developing high-bandwidth, high-capacity network storage on demand to accommodate this data. Radio astronomers around the world will benefit from these developments in next-generation eVLBI. Furthermore, new developments of the EVN technologies advanced by JIVE are essential for new telescopes. The high level of automation and distributed architecture are also feeding into the design of the square kilometer array. Additionally, these developments are crucial for various planetary science missions such as ESA's Venus Express and space-based VLBI telescopes such as RadioAstron. Work by JIVE is pushing the envelope of Europe's ICT infrastructure.
It has been demonstrated that fundamental science has a healthy impact on the viability of our economy. And it's not hard to imagine how the techniques that we deploy in eVLBI will influence other sciences, education, communication, and even entertainment.
JIVE, forging a path to the future of radio astronomy.